This talk overviews a review entitled 20 Years After: Scaling Relations in Oxygen Electrocatalysis and Beyond. It hints to the fact that the scaling relations appeared in the literature 20 years ago, as well as refers to the sequel to The Three Musketeers by Alexander Dumas. The authors are Vladislav, Rytms, Jan, and Nadezhda. The review is available at Chemarchive. Let me begin with a quote of Leo Tolstoy from War and Peace. When an apple has ripened and falls, why does it fall? Because of its attraction to the earth, because its stalk withers, because it is dried by the sun, because it grows heavier, because the wind shakes it, or because the boy standing below wants to eat it. Nothing is the cause. All this is only the coincidence of conditions in which all vital organic and elemental events occur. Let me reformulate this quote in relation to electrocatalysis. When an oxygen molecule adsorbs and is reduced, why does it turn into water? Because the potential drives electrons to the surface, because the adsorption energy is just right, because the surface geometry suits the intermediate, because the proton supply is fast enough, or because the girl measuring the RDE wants so. Nothing is the cause. All this is only the coincidence of conditions in which all catalytic events take place, limited by the scaling relations. Across scientific fields, progress often reveals a hidden constraint. This slide shows 4 cases: a combustion engine, a wind turbine, a solar panel, and a catalytic site in a GSO catalyst. Each represents a point in history where performance began to plateau. The pattern is familiar. A promising technology emerges. Then, a physical or chemical principle sets a hard limit on unit-level efficiency. To move forward, we don't break the rules, we change the system. We rethink what the unit is and how it works. For engines, combined cycle designs raised efficiency beyond what a single thermal cycle could achieve. In photovoltaics, tandem cells surpassed the Shockley-Kayser limit for single absorbers. Wind energy advanced not just by improving blades, but by changing tower height and park level layout. Electrocatalysis now stands at a similar turning point. Scaling relations set a ceiling on the performance of single-atom sites. But by introducing multi-atom sites allows to circumvent the limit. This presentation builds on that idea. We classify strategies that manipulate scaling relations in analogy to breakthroughs in other technologies. The central theme is simple. Unit-level limits exist, but system-level solutions remain open. I will guide you through the basic concepts we will need for the rest of the talk. These include overpotential, scaling relations, reaction mechanisms, and the activity volcano. Let us begin by examining what defines the efficiency of electrochemical energy conversion, using the example of water splitting and its reverse in a fuel cell. In the left-hand panel, we show standard polarization curves, current as a function of potential, for the fuel cell reactions. Rather than discussing hydrogen, let us focus attention on the oxygen side, where the main energy losses occur. Here we have oxygen evolution and oxygen reduction reactions. Specific points on these curves mark the selected power potentials: 10 mA per square centimeter for OER and 3 mA per square centimeter for OR. These current densities serve as benchmarks and allow direct comparison of catalyst performance, all referenced to PT 111. Using these values, we also introduce overpotential, the difference between the thermodynamic equilibrium potential, 1.23 volts for OR, and the actual potential needed to maintain the benchmark current. The overpotential quantifies the extra driving force required to overcome the thermodynamic, kinetic and steric limitations inherent to the catalyst and the interface. Considering efficiency, THR arrows indicate 2 key values: the applied electrolysis voltage and the fuel cell voltage under load. Taking the ratio of these voltages yields the round-trip efficiency. In the right-hand panel, take a look at the timeline of the highest recorded power potentials for OR and OER over the last decade. We distinguish between platinum group metals, PGMs, and metal nitrogen carbon, MNC, catalysts to highlight the advances in both classes. Despite this progress, a clear gap remains between the best OR and OER values, hundreds of millivolts wide. This defines the practical efficiency loss that even our best systems cannot yet avoid. As we shall see, theory connects this limitation to the energetics of reaction intermediates through the scaling relations. Let us now zoom in on the oxygen reduction reaction and extend the perspective over 20 years. You see the highest reported ore over potentials. These data points define the frontier of electrocatalyst development, revealing a gradual approach toward the state-of-the-art limit near 0.3 V. Next, we shift to computational predictions that arrive at the same value. The shown points are calculated from adsorption energies of reaction intermediates and mapped onto the so-called volcano, which reflects the Sabatier principle. Optimal performance emerges from binding the O intermediate neither too strong nor too weak. The three-dimensional volcano is a theoretical framework. It captures a multi-dimensional energy landscape and serves as a predictive tool for catalyst design. Beneath all this lies conceptual chemistry, the reaction mechanism. As an example, you see both associative and dissociative pathways of ore on a metal nitrogen-carbon catalyst. On the right, we collect empirical observations. On the left, we present theoretical models. Above, we show what can be measured in the laboratory. Below, what can be simulated with computation. All of these perspectives are connected by a shared constraint, the scaling relations. Let us take a broader perspective on how the volcano concept emerged and became widely used in electrocatalysis. You see a timeline that tracks the growing number of publications in the past 20 years. It reflects the rising interest in the oxygen reduction reaction, but also shows how ideas like the Sabatier principle and scaling relations gain traction. The notion of a volcano plot, once a niche idea, has become a central organizing tool for catalyst design. Next, we visualize the ideal catalyst. An ideal ore catalyst would deliver a limiting potential of 1.23 volts, meaning it drives the full reaction at equilibrium with no overpotential. This is a theoretical extreme, not yet realized in practice. Instead, most real and virtual materials fall along a constrained path, the magenta line, dictated by the OU scaling relation. That line separates the best ore and OER catalysts. To illustrate this concept, I use an artistic rendering of a volcano. The volcano metaphor tells us that one cannot climb a volcano from just any side. There are natural boundaries and accessible paths. Likewise, in catalysis, we are bound to move along certain thermodynamic paths set by scaling relations. The magenta line is one such path. It defines the only accessible route up. While the ideal catalyst at the apex remains in view, our climb is restricted to this narrow route. That is the conceptual power of the volcano. It shows us where we are, where we could go, and why we cannot get there directly. The mechanism can be complex even for such a simple 4-electron reaction as oxygen reduction. The pathways of such reaction are numerous and sometimes overlapping. These include proton-coupled electron transfers, side reactions, associative and dissociative steps. The schematic reflects the level of ambiguity we often face when assigning mechanistic details. And yet, despite this complexity, the description of catalytic performance often reduces to a few key quantities. Here you see a set of linear relationships between adsorption energies. U. These correlations are known as scaling relations. Scaling relations couple adsorption energies through the chemical nature, valence, and coordination of reaction intermediates. Typical intermediates are O, and U. These relations collapse the multidimensional surface chemistry onto a single axis. No matter how intricate the mechanism appears, it is these adsorption energies that to a large extent determine the limiting potential. To begin the discussion, let me clarify the most essential steps of what happens during oxygen catalysis. The oxygen catalysis of a catalyst can proceed via associative or dissociative mechanism. In both cases, even at high pH, the key intermediates are U. In the associative mechanism, O adsorbs intact and is reduced step by step. This pathway dominates in most known catalysts because it operates on a single active site. That is common across surfaces like PT, 111, or MNC materials. The dissociative mechanism, in contrast, involves an early OO bond cleavage. This requires at least two neighboring atoms to accommodate the resulting O and O fragments. As a result, It has been considered less common but remains an attractive alternative, especially in systems where dual atom sites are present. Each intermediate, U-O-O, has a characteristic adsorption energy. In principle, we would like to tune each of these independently to optimize each elementary step. But in practice, we cannot. Their energies are correlated. This is what we call a scaling relation. Scaling relations appear as straight lines when we plot the adsorption energy of one intermediate against another. That means if you change one, the other changes with it. The correlation is linear and surprisingly robust. It holds across a wide range of catalyst surfaces. Why does this happen? The slope of the scaling line reflects how the bonding changes between the intermediates. For example, forming operator U from operator O involves adding an OO bond, which introduces roughly one additional bond and character, giving a slope near 1. For operator O vs operator O, where two operator O-like fragments form an O molecule, the slope is closer to 2. The intercept captures the intrinsic thermodynamic offset, bond dissociation energies, solvation effects, electrostatic stabilization. For example, the UO scaling has an intercept around 3.2 electron volts. That value represents the difference in forming an OO bond versus an OH bond on the surface. In most studies, we extract these relations from DFT calculations. Using the adsorption energies, we can analyze the predominant coverage and free energy plots to predict the overpotential. The methodology is described details in Fundamental Atomic Insight in Electrocatalysis. For now, let us focus on the volcano and scaling relations. Let us now turn to the volcano plot. This theoretical framework that captures the performance landscape of catalysts. The surface of the volcano defines the chemical space. All possible combinations of adsorption energies that a catalyst might have. Catalysts sit on this surface. Their position reflects their binding strength. Too weak, and they cannot activate the reaction. Too strong, and they hold onto intermediates too tightly. The optimal performance lies at the optimum where the binding energies are just right. This is the Sabatier principle in visual form. We construct this model by calculating the free energy change for each step in the OR mechanism. Using scaling relations, we reduce the number of variables and express the entire system in terms of a single descriptor, often increment G_oxygen monohydride. But here's the constraint. Catalysts do not roam freely across the volcano surface. Scaling relations impose specific routes. The magenta line represents the conventional path dictated by the scaling relation for the associative mechanism. The green line suggests a different relation for the dissociative mechanism. This is why the volcano remains such a powerful metaphor. It shows us not only where the optimum lies but also the limited paths available to reach it. The shape is continuous, but the movement is restricted. The challenge is clear. Stay on the path and optimize within it or find an alternative one. To better understand how this framework works, let us break it down through a sequence of views. We begin with the volcano rendered as a three-dimensional surface. All combinations of increment G_U and increment G_O lie within this space. To evaluate performance, we define a slicing plane. This is the set of catalysts consistent with the UO scaling relation. That intersection creates the magenta path. From here, we extract two projections. The first is the side view, the climber perspective. It shows the limiting potential as a function of a single variable, usually increment G_O. This is the classic volcano plot. A peak at the optimum, flanked by performance losses from too weak or too strong binding. The second is the top-down view, the helicopter perspective. It shows overpotential as a contour map in the increment G_U versus increment G_O plane. You see the full landscape of possibilities. The star at the center marks the theoretical optimum. Specific catalysts, however, fall along a narrow diagonal, the scaling path. These two projections tell the same story from different angles. The top view reveals the goal. The side view explains the constraint. Computational fellows and theoreticians to remember that every reaction happened dynamically. The reason we do not explicitly model such a complex process is not because we cannot, but because it is not necessary for identifying the key chemistry. In fact, before the discovery of scaling relations, Researchers did simulate very complex interfaces at the very limits of their resources. The real reason we simplify these visualizations down to a volcano is that, in nature, there are only a few rate-limiting steps, which in chemical terms are very simple. The scaling relations likely describe exactly that crucial chemistry. In practice, here is how a predictive computational workflow looks. We start with the compositional space, create models, predict their stability, evaluate adsorption energies, and work down to predicting current density. For each stage, we use appropriate tools, such as the free energy diagram and microkinetic modeling, and we choose the right computational approach. For calculations, this might be density functional theory or machine learning. That does not matter much these days. It is also worth noting that there are two types of scaling relations. Thermodynamic scaling relations connect adsorption energies, while kinetic scaling relations connect reaction barriers. For further details, I recommend the listed articles. For the sake of simplicity, let us now focus solely on thermodynamic scaling relations. I will introduce a few key terms that will be used throughout the discussion. These include tuning and braking, switching and pushing, circumventing and bypassing, and the concepts of coplanar and cofacial dual-atom catalysts. Understanding these will make it easier to follow the strategies and examples in the upcoming slides. When I first started researching scaling relations, I found it incredibly confusing. There were so many different terms, often used inconsistently, making it hard to grasp what they actually meant. Then came along this article. What we talk about when we talk about breaking scaling relations. By Federico, who was inspired by the book, What We Talk About When We Talk About Love. So, Federico raised two questions. Do we know of any materials that unmistakably break scaling relations and, more importantly, if the breaking of a problematic scaling relation is the end of all troubles in electrocatalysis? These questions guided me and co-authors in creating a classification of all shown terms. If we sort these terms in chronological order, a clear story emerges. The concept of scaling was first introduced by Jan Rosmeisel in 2005, with its first reference as scaling by Bild Peterson in 2007. The scaling is a linear relation between adsorption energies of similar adsorbates. In 2011, Yver Stevens and colleagues introduced the term tuning, referring to reaching the volcano edge within the OU scaling relation. In 2014, Montmore and Medlin proposed breaking, meaning a deviation from the OU scaling relation. In 2015, Vovidik and Norskov introduced circumventing, meaning any departure from the OU scaling relation. In 2016, Bush and co-authors used the term switching for an alternative mechanism involving combined adsorption sites, effectively switching between mechanisms and scaling relations. Most recently, in 2024, we introduced bypassing, referring to the use of two states to decouple adsorption energies entirely. All these terms describe manipulation of the scaling relations. Here we see a timeline showing, in pale, the lifespan of each strategy starting with its conceptual definition. The solid lines indicate when the strategy was experimentally verified. On top, you see progress in experiments. In 2004, the first experimental volcano plot included work function and activity. In 2011, the discovery of single-atom site catalysts marked a major step. In 2016, the experimental volcano plot included predominance potentials as an analog of adsorption energy versus activity. In 2018, the discovery of dual-atom site catalysts with well-defined interatomic distances was another breakthrough. Finally, from 2021 onward, spectroscopic insight into the mechanism of catalysis has been critical for verifying manipulation strategies. Below, you see progress in calculations and theory. The introduction of the scaling relation in 2005 is the starting point for everything. In 2011, computational models of single-atom site catalysts appeared alongside their experimental discovery. In 2016, the concept of the 3D volcano was introduced. From 2018, dual-atom site catalysts were probably more thoroughly studied on computers than in the laboratory. Finally, in 2024, a computational proof of concept showed that the scaling relation could be bypassed, completing the current story. Let us now look more closely at dual-atom site catalysts and their role in manipulating scaling relations. These catalysts come in two main geometries, coplanar and cofacial. Coplanar DACs position two active metal centers within the same plane, often fixed by a rigid coordination environment. This geometry allows precise control of the interatomic distance, enabling tuning of adsorption energies via varying metals, breaking of the UO scaling relation via stabilizing interactions, and switching to the dissociative mechanism when the distance is optimal, neither too close nor too far. In some cases, coplanar DACs can also realize the pushing strategy by stabilizing O relative to O. Cofacial DACs place two active metal centers facing each other, often within macrocyclic or cage-like structures. Here, the interatomic distance can be adjusted more freely, for example through linker rotation, offering similar opportunities for tuning, breaking, switching, and pushing. However, experimental demonstration of mechanism switching or pushing in cofacial systems remains limited. We've grouped our approach into 5 strategies: tuning, breaking, switching, pushing, and bypassing. Each one changes how reaction intermediates interact with the catalyst surface, but in its own distinct way. In the next part, I'll walk you through what each strategy means and how it works. One of the most common strategies for boosting catalyst performance is tuning the O adsorption energy. In the associative pathway, we deal with U, O, and O intermediates. On a volcano plot, adjusting the O adsorption energy lets us walk along the UO scaling line without changing its slope. Each catalyst has a characteristic adsorption energy that fixes its spot on the volcano. By fine-tuning, we can nudge it toward the sweet spot, usually an OH adsorption energy between 0.86 and 0.96 electron volts, corresponding to a theoretical overpotential of 0.3 to 0.4 V. This approach is well explored, from model single crystal surfaces to single atom metal nitrogen-carbon catalysts. The microscopy image here shows a typical metal N site, while the model illustrates the flexibility in its composition. Macrocycles, like iron phthalocyanine on nanotubes, are especially adaptable, achieving an overpotential of 0.28 volts, close to the theoretical maximum. Tuning doesn't break scaling limits, but it's reliable, effective, and, for most studied catalysts, still the only practical way to manipulate them. The second strategy is what we call breaking the UO scaling relation. The aim here is to selectively stabilize the U intermediate without affecting O. If we can do that, say, by approximately 0.3 electron volts, we shift the scaling intercept from the usual 3.2 electron volts to about 2.9 electron volts. On the volcano plot, that means a potential drop in the OR over potential to 0.1 to 0.3 V. How do we achieve it? 2 common ways: hydrogen bonding from a base, shown here in the cycle, or introducing a second metal atom to interact with U. The pathway is still associative, but U gets an extra boost in stability. This isn't just theory. In 2023, Zhang and co-workers used an Fe PMNC catalyst where PO sites hydrogen bonded to U. In 2024, Sun's group made a dual cobalt molecular catalyst. Spectroscopy confirmed U as the active intermediate and measured overpotentials as low as 0.23 V. The key point: breaking can outperform tuning, but only if you're already near the volcano edge. When a limitation is dictated by the reaction mechanism, one way to bypass it is to switch to a different pathway. For OR, that means moving from the associative mechanism to the dissociative one. Switching requires 2 active sites, so intermediates can adsorb separately, and O can split into O and O. On the volcano plot, you see this as a slope change from 1 to 3. But here's the catch: 2 sites alone won't guarantee improved performance. The range where switching actually reduces overpotential is very narrow, centered around an adsorption energy of 1.1 electron volts, which corresponds to a minimum overpotential of about 0.1 V. Also, the site spacing has to be just right, close enough for cooperation, but not so close they interfere. Examples exist. In 2021, single-atom PT on manganese 4 oxide showed no detectable U intermediate in spectroscopy, consistent with a dissociative pathway. In 2024, MULTIVALENTFE2N6 dual-atom MNC sites were shown to do the same. So, switching is possible, but it's a precision move, only effective in a very specific sweet spot. Pushing is a close cousin of braking, but instead of stabilizing U, here we stabilize O relative to OO. It applies to the dissociative mechanism, targeting the O-OO scaling relation. The effect is twofold. We not only shift the intercept but also change the slope, bringing us closer to the ideal catalyst line. One way to achieve this is through hydrogen bonding to the O-O intermediate. Another is exploiting geometry, such as the curvature effect in coplanar active sites. In fact, DFT calculations for curved multivalentco1n4 models predict overpotentials as low as 0.1 V. In short, pushing is braking for the dissociative route, but unlike braking, it hasn't yet been confirmed experimentally. The last strategy is the most ambitious, completely denying the scaling relation. Here, the idea is to decouple the adsorption energies of key intermediates. All it takes is two distinct catalyst states, each with ideal adsorption energy for a different step in the reaction. If we can switch between them during the catalytic cycle, we could in theory achieve ideal behavior, with zero overpotential. On the volcano plot, this isn't about moving along the slope at all. Instead, it's like tunneling straight to the center and jumping right to the very top. Nature has already mastered this trick. In cytochrome C oxidase, conformational changes create the perfect environment for each reaction step. And theory shows we might be able to copy it. Computations predict that a 2-multivalentco1n4 dual atom catalyst could adopt two different geometries, each optimized for a different intermediate. Bypassing, then, is the ultimate goal. A way to break free from the rules entirely, using inspiration from both enzymes and modeling. To bring it all together, we've organized the different strategies for manipulating scaling relations into a single, systematic framework. Here on the chart, the star marks landmark virtual catalysts, like PT-111, for tuning, while the circle marks landmark real catalysts, such as cytochrome C oxidase for bypassing. Looking side by side, you can see the clear differences in mechanisms. This makes it much easier to decide which strategy to apply, or to explain the activity of a new catalyst, based on where it fits in the classification. Now, this framework is conceptual. In practice, we often work with specific, well-known effects. For metals, alloys, and high-entropy alloys, these include the strain effect, the ligand effect, and the cocktail effect, all of which operate within the limits of the tuning strategy. With these effects, we're deliberately manipulating the UO scaling relation, and mastering them is exactly what allows us to design catalysts that are both more active and more selective. Let's look at an example of how structure controls the adsorption energy of intermediates, using MNC catalysts. With a single active site, the UO scaling relation holds, and all we can do is tune it. But if we move to dual atom sites, new options open up. We can now tune, break, and even switch. Add in structural features like curvature, and the toolbox expands further, making pushing and even bypassing possible. The energy diagram here sums up this idea at a glance. In the next section, we'll unpack each of these cases in more detail. Now we are ready for an outlook. First, I will revise the Sabatier principle in terms of weak versus strong binding. Next, I will introduce an emerging geometry principle for far versus close adsorption sites. Let's summarize the strategies using correlation equations with characteristic slopes and intercepts. Braking is just lowering the intercept, as well as switching when we go from switching to pushing. The stabilization can be approximated by 0.3 electron volts. Out of the 5 general strategies for manipulating scaling relations, 4 already have examples in the literature or in nature. For instance, PT-Ni alloys from the early 2000s exemplify tuning. Most of these concepts have moved beyond theory and into experimental testing, with only pushing still awaiting its first confirmed case, and bypassing requiring laboratory implementation. This brings us back to the Sabatier principle. It states that binding between the catalyst and intermediates must be neither too weak nor too strong to achieve optimal activity. In all the cases discussed, the adsorption energy of O is the key descriptor. The lower the overpotential, the closer the O adsorption energy is to the ideal value of about 1.23 electron volts. We see progression from approximately 0.9 to 1.0, then 1.1, and finally 1.23 electron volts. Literature suggests that a principle emerges for dual atom site catalysts. The distance between active sites must be neither too far nor too close. If the sites are too far apart, they cannot jointly stabilize O or accommodate U after dissociation. If too close, intermediates may repel each other. The optimal distance allows each site to contribute in a complementary way, enabling tuning, braking, switching, and pushing with maximum efficiency. Similar to the Sabatier principle, this new principle applies to both thermodynamic and kinetic scaling, and to both coplanar and cofacial catalysts. The most important data in the review is gathered in the table: strategy, limiting scaling, optimal O adsorption energy, and distances, given for coplanar, with cofacial values in brackets, along with evidence from literature and estimated lowest overpotentials, from 0.3 volts for tuning to 0.1 volts for braking and switching, and 0 volts for bypassing. Of course, questions remain even after such an extensive review on scaling relations. The first question is whether high-entropy materials can break the O-O scaling relation. Alloy development since the 2000s has shown that strain and ligand effects can tune adsorption energies. High-entropy alloys can optimize the distribution of adsorption energies, which is not trivial. Initially, this seems to be tuning, but changing the environment around the active site could also allow braking or switching. Literature hints exist for metal alloys and oxides. This is definitely ample space for research. Another question that bothered me personally while doing this review is how to compare different materials, surfaces of metals, metal alloys, high-entropy alloys, MNC catalysts, and zero-dimensional molecular catalysts. For platinum, a stable O and water layer forms around 0.9 volts, but single-atom or molecular catalysts lack this structure, and solvation differs. In DFT, we compute potential energy, then add corrections for entropy, zero-point energy, solvation, and more. A recent paper by Favaro compared activities of various PHT halocyanides, showing that while the calculation method is the same, correction terms differ. Thus, in principle, it is possible to run calculations and apply empirical corrections to put all catalysts on the same free energy scale. Before comparing very different catalysts, we need to understand platinum group metals and alloys. Some experimental platinum data shows a slope of about 1.2 when plotted against calculated adsorption energies. I cannot explain that from the literature. In calculations, we apply scaling relations, build free energy diagrams, include barriers, and run microkinetic modeling. These cut the volcano apex but do not match the experimental slope. Accounted for the pH effects also cuts the volcano apex horizontally. That looks promising, and one may think we should make modeling more and more realistic, like with molecular dynamics, to capture the whole complexity. I still hope for a simpler explanation in terms of the scaling relation. That is actually a valid thinking approach and is called essentialism. The explanation may come from scaling relations between overlooked intermediate states. And we might find it by thoughtfully applying specific effects. Check https://www.science-direct.com/science/articles/p/s24519103230017581. 1. 2004 paper by Norskov explained experiments and proposed a framework as a predictive tool. 2. However, we now see in evidence from experiment that there is some limitation that is extra to the CHE framework. Or is it? A. To fix the situation, Norskov suggests augmenting the scaling relations with microkinetics in a constructivist way. B. Essentialism. Here is a map of effects from Vavadic and Norskov. There are electronic effects and structural effects. We call them geometric throughout the review. Note that many effects fall in between. Examples include ligand, strain, and cocktail effects. Remember that these can have negative and positive impact on activity. The outcome of each effect can be rationalized in terms of the scaling relations, as we have already discussed. Let us turn back to the most general and conceptual level. There are only 5 strategies for manipulating scaling relations: tuning, breaking, switching, pushing, and bypassing. Other terms commonly seen in the literature are overcoming or circumventing, and they perfectly fit here. Overcoming is transition from tuning to breaking, while circumventing is any other strategy rather than tuning. We propose using manipulating because it includes tuning. Most of the recent progress was made with this most common strategy. The main message of this talk is to use the presented classification to think strategically about manipulating the scaling relations in search for new catalysts.